Hello everyone, welcome to Chapter 2. This is Dr. Kofelt and I will be talking about atoms, molecules, and ions in this section. So we're going to look at the atomic theory and some of the history of the discovery of the ions and things like that. And I'm not going to spend a lot of time on that, just so you know. If you want to know details about that, feel free to go ahead and investigate that on your own. But I just, you know, we have such little time and so much to cover in this section that I just don't feel like that's time well spent. Okay, so these are the learning objectives, and you have these in your Blackboard shell as well. And so, having said that, let's get started for part one, where we're going to talk about the atomic theory. We're going to look at the three hypotheses associated with Dalton's atomic theory, and that's particularly what you are going to be held responsible for. So, first of all, let's look at the atomic theory, and this is Dalton's atomic theory. Okay, so the three major postulates of the atomic theory here are: elements are composed of extremely small particles called atoms. Compounds are composed of atoms of more than one element. And a chemical reaction rearranges atoms. It does not create or destroy them. So remember that matter and energy cannot be created or destroyed. So this came about through a lot of different ones, and so what I want you to do is I want you to pay attention to who did what. You don't have to remember what the dates were or anything like that. And I'm going to tell you what you're going to be responsible for. So this chapter in the book goes through some more details than what we are really interested in. So the first person we're going to talk about is Proust. Proust gave us the law of definite proportions, and that means that there's different samples of a given compound contain the same elements in the same mass ratios. So basically what we're saying is, if we have a molecule like CO2, CO2 is going to always combine in the same mass ratios and the same mole ratios. Okay, that's all that means. All right, and so what happens is that you'll see that like we'll look at ratios with carbon dioxide. If you have 123 grams of carbon dioxide, it's going to be in the same ratio as if you had 50 grams of carbon dioxide. So that's all that's saying. So it's going to be the same ratios. So this law of multiple proportions says that the masses of one element that combine with a fixed mass of the other elements are in ratios of small whole numbers. What? Okay, so that just means that, like, if I've got carbon dioxide, it's going to combine mass-wise in a ratio of 2.66 grams of oxygen to 1 gram of carbon. Carbon monoxide, however, will combine in 1.33 grams of oxygen for every 1 gram of carbon. And that makes sense because there's 2 moles or atoms of oxygen and CO2, but there's only one in CO, which is carbon monoxide. So how we do that is, since you look at two different things, okay, so we look at CO2 and look at CO. And the ratio between those, we said, is looking at the oxygen, 2.66 to 1.33. If you divide that fraction, you're going to get a 2-to-1 ratio. Okay? So that means in carbon dioxide, you're going to have a 2-to-1 ratio. So it sounds a little confusing, but it's really not. So I'm going to show you this worked example here. So in the case of water and water is H2O as opposed to peroxide, which is H2O2. They're both comprised of the same atoms, hydrogen and oxygen. When water is decomposed into its constituent elements, that is hydrogen and oxygen, you end up with 0.125 grams of hydrogen for every 1 gram of oxygen. However, when hydrogen peroxide is decomposed, it produces 0.063 grams of hydrogen for every gram of oxygen. So to determine the whole number ratio, what we do is we do grams of hydrogen in water versus grams of hydrogen in peroxide. And when we divide those out, we get approximately a 2-to-1 ratio, which is what there are. There's 2 hydrogens and 1 oxygen in H2O. Hopefully that makes a little more sense. But that's basically the multiple proportions, the law of multiple proportions. And then in another sample of this, you can try this one yourself, is comparing sulfur dioxide and sulfur trioxide using the grams of each. And you'll see that in this case, you're going to get 3 to 2 for grams of oxygen to sulfur, and that's because you have an SO3 in one of them and an SO2 in the other. Notice that this one had a 1.5, and you can't have a partial, right? You have to have whole number ratios for this to work, and so we have to multiply that by 2, and that's where we get the 3 to 2 ratio. This one's very complicated to understand. Don't worry about it. If this is kind of like your head spinning a little bit, we will go over the other ones that are a little more important than this one in part 2.